Good morning, Irvine. Happy Wednesday to you. More in detail, happy Woden's Day to you. Wednesday is Woden's Day, right? That's the root. Who was Woden? Got the day named. Who was Woden? A god, right? Teutonic or Norse or both. The god of passionate inspiration. Passionate inspiration. In other words, a person who enjoyed doing physics, or a god who enjoyed doing physics. So let's have some passionate inspiration day and have it be Woden's Day and have a good time with it. Okay, so let's see. Now I suggested that you look in the book for an example to help calculate the electric field in some geometry, and I got a small sense from some of you that you'd like me to do it to show you my perspective on how to do that kind of calculation. So I'm going to do that now, okay? So we're going to do a little bit of, before we do our first examples here, we're going to do a little bit of calculational stuff. So let's look in more detail on charged rods. Predictions for more detailed charged rod predictions. The kind of thinking, the conceptual approach here that I'm going to try to show you to have the physics guide the math, you'll be able to use for any geometry you do these kind of calculations for. And the thinking about it, the way the physics will guide this math, should also guide our understanding of electric flux and how we approach what is called Gauss's law, which is another way of stating Coulomb's law. So let's start with our charged rod that we're thinking about. And this charged rod has some amount of charge on it, lambda coulombs per meter. I'll put some plus signs here just to indicate that, but it could be minus charges, right? Do the charges have to be uniformly distributed? No. So it doesn't have to be, but let's look at the physics where things are fairly straightforward, and we'll use a straight rod, uniform charge. We're going to go out somewhere from that rod to this point I labeled as P. So point P. And that is some distance x out there. I'm going to try to find the total electric field at that point x. So let's look to begin with. If I have all of these charges here, maybe there's some little chunk of charge. And I'll indicate it by a little cylinder of charge here. That's some distance out here, and its height from that point x is y. And that little chunk of charge will make a contribution to the electric field. Let's label it as a differential contribution, dE. And I see there's an angle here. Let's call it theta. I think that's the way I drew it last time. We're going to imagine a rod. So rods can be any kind of length you want them to be. And we noticed from yesterday that if the rod was very short, if the total length of the rod was small compared to x, then we could treat this problem as a point source. That all the charge was a distance x away, and we could do that, and boom, the math just got very simple. We just write down Coulomb's law, and then F equals QE. The electric field is the force over the test charge, force per unit charge. On the other hand, if the rod goes out to plus and minus infinity, well, that's kind of an easy limit to think of too. So we have the extreme limits then of the rod being very short or the rod being infinitely long. We'll go ahead and calculate for the infinitely long rod. And the rod could be anything in between. So if the rod was anything in between, that angular extent for theta could be something in between 0 and 90 degrees up there and something between 0 and minus 90 degrees down below. And it's whatever those limits are. The nice thing about integrals is you put the lower limit down at the bottom and the upper limit at the top. You go about doing your symbolic calculations and then plug those in. Does that sometimes get really messy in the final answer? It does, doesn't it? So that's just part of life. Sometimes it gets complicated. Let's imagine now that we have an infinite extent on the rod. So the electric field contribution here, if I draw an extension of that axis horizontally out like that, and now where I've put my finger, what is that angle? It's also theta, isn't it? So we recognize that's theta on the other side as well. And I can break the electric field, which has magnitude and direction, down into components expressed in whatever coordinate system I wish. So I'm going to use a y-axis going up and an x-axis going horizontally to the right, so I can talk about x and y components of that electric field. So we have dE in the x direction is going to be dE times cosine of theta, and the dE in the y direction is going to be dE times sine of theta. If I have an infinitely extended rod, then for every little element dy up above, let's put that element of length dy up above, label this extent as dy. There's some charge in there. And if I have an infinite rod, then this, for every element of charge that's in that dy up above, there is correspondingly a mirror image element of charge down below that's in a dy chunk also, and those two will cause the y components to cancel. So I know that the integral of the dEy's adds up to Ey, but that's equal to 0. That kind of calculus is a lot of fun to do. Let the physics tell you what the answer is. You don't have to calculate all the little details in it. The x one, on the other hand, let's ponder that one through a little more and arrive where we need to. Okay. So to get the total x component of the field, I need to go from, where do I need to go? Let's go from y equal minus infinity to y equal infinity. And then we're going to go through calculating the electric field. I got a 1 over 4 pi epsilon naught. I have the amount of charge that's in the chunk at dy divided by, what's the distance from the point P to the dy element? That's the hypotenuse of that triangle. So the distance along the hypotenuse of that triangle is x squared plus y squared square rooted, but then I have to square it. Remember, it's r squared for the distance factor in the Coulomb's law. Okay, we've still got this 1 over 4 pi epsilon naught dq, the amount of charge that's in that little chunk. Well, just like when we took, was it your belt?
Yes.
When we took your belt and cut it into chunks, we could know what the total mass was. We could figure out what the mass per chunk was. Now we're going to do charge per chunk, so that's going to be lambda times dy. And down here is x squared plus y squared. Okay. we also have to put in the x element of it. So we have to put in our cosine theta factor that we have for looking at the x component. Okay, we have now some algebraic stuff in there, your x squareds, y squareds, and we also have a theta in there, your cosine theta. So we've got, let's see, doesn't theta depend on y? Yes. Or doesn't y depend on theta? Yes. So you have a choice. Neither one of them is constant, but they are a function of each other if you want, or you can pick. So you can either pick to do this integration by going through the algebraic side, or you can pick to go through the trigonometry, geometry side. I'm going to do the theta side. I like that one better for this. Okay, so if we look there, we see that tangent of theta is y over x. Tangent's opposite over adjacent. So that tells me that y is equal to x tan theta, and dy is equal to, what's the derivative of tangent with respect to theta? Secant you shall find, right? So secant squared theta d theta. And secant is, what's secant? Is a flipped over cosine, right? Okay, so now let's see. Oh, let's also look at this x squared plus y squared factor. That's x squared plus x squared tangent squared theta. So x squared times 1 plus tangent squared theta. And that's x squared secant squared theta. Okay, now we can plug her in. Ex is, and we have an integral from y equal minus infinity. Let's leave it saying that right now and then figure the next step to y equal infinity. I got the 1 over 4 pi epsilon naught. I want to plug in for lambda dy is x secant squared theta d theta. I've got the cosine I've got to keep there. And I've got x squared secant squared theta down here. We doing okay? What happens to this stuff? Look how the secant squareds canceled each other. Isn't that lovely? So let's see now. Let's go integral. Now let's pull some constants out. Can I pull out the 1 over 4 pi epsilon naught? That doesn't depend on anything, right? Can I pull the lambda out? Okay, can I pull the x out? Oh, you think about that a little bit, right? No, this is an integral going as a function of y or theta. X is held constant at this point. It's not part of what's getting integrated. So that can come out. Got x upstairs and x squared downstairs. So I've got a lambda. I got a 1 over 4 pi epsilon naught, and I've got a lambda over x, okay? And then I've got a integral cosine theta d theta. Let's now let the physics guide us here. We're going from y equal minus infinity. What's the theta value for that? It's down there, so it's a minus pi over 2. Right? So theta is minus pi over 2. And up above, to go to infinity, what's the theta value there? Pi over 2. Okay? And when you integrate cosine, what are you going to get? You get a sine factor, right? And the sine evaluated at 90 degrees is what? 1. Sine evaluated at minus 90 degrees is minus 1. You got a A 1 minus a minus 1, what do you get?
2.
Dose, 2. Okay? So we see that the answer is 1 over 2 pi epsilon naught lambda over x. Now, there would be another way to think about that set of limits if you want. We can look at it and recognize the symmetry of the problem. Very often in nature there are symmetries, or very nearly symmetries. And we could say, oh, we could go from 0 to pi over 2, 0 to 90 degrees, and we get the same result as going from 0 to minus 90. So you could have theta equals 0 as the lower limit, theta equal pi over 2 as the upper limit, and multiply the answer by 2. Either way gives the same result. The physics is unchanged. Your math perspective was different. You can take the symmetry and just do half the integral. Sometimes that's real handy to do. So you get to pick, and either way you arrive at this kind of answer. Oh, I can see you're going to have to review that calculus stuff a little more, aren't you? And maybe even, wasn't that a little quick to go from this guy over to here? Do you remember that theorem? That stuff, didn't they teach that to you in, what grade do you get that stuff? 11th grade, 10th grade, 9th grade. In the high school, right? Because it's important stuff. It's high school, right? It's useful, the stuff you learned there. Okay? So reinforce it by, isn't there a little appendix in the back of the book? Right? And with electrosurgery, you can remove that appendix and have it handy wherever you want. Okay. This way of thinking will work for any of the electric field calculations you might like to make. For any predictions, if you know the distribution of the charges, you can apply this kind of approach to get the total electric field at any location. The other key that people often stumble on is you go x and y, oh, these are all variables. Well, it's true. Once we get to the end, you may move x around as you like to find what its electric field is further out. But x is a constant in terms of this calculation. You're fixing the point that you're looking at. You're moving where the charge is that you're calculating the contribution to. Okay, so the picture we get from that rod is an electric field that points out, everywhere outward, and that gets smaller as you get further out. So you might do something like that with changing the length of the arrow. And so if you go twice as far out, the arrow should be half as long. Okay, so that means I did it a little bit too slow a diminishment here. But something like that. And notice, doesn't this look as well just like a sheet from the side? So if I were to have a sheet of paper, like what we showed for that calculation, and you make a drawing of the sheet, doesn't the drawing look pretty similar? So you need to be very careful. Once again, when you're looking at drawings and doing your physics calculations, you need to be very careful to think, am I talking about a sheet of charge here or a line of charge? What's the drawing represent? So be careful to include that kind of thinking instead of just looking at the drawing, grabbing a nearby formula and saying, oh, I'm going to go on with it. No, think about it, think about it. And the same thing happens on the left for the electric field diminishing. We can make a drawing then to help reinforce, as a function of distance, the magnitude of the electric field drops as 1 over r, right? Going as 1 over r, and in this case, we're using x for that distance represented by the radial separation of P from the line of charge. Oh, the excitement, the excitement. If we were to view this from above, so here's our, for example, we could think of this as a line of charge. Now let's view it from above, okay? Got the picture? What do you see? From above, if we did the drawing from above, here's the rod, and this is from above, a rod from above. So view the rod from above. Now the electric field points everywhere outward from the rod like that. And down where I've drawn as well, just for symmetry. Try and get that showing, get that too. Okay. Now, I guess this line of argumentation is going to be a little cagey. Do you see the cage that I have here? Suppose that I have the rod and I put the rod like that. You see the geometry? If we think about the electric field coming out of the rod, it's everywhere radially outward or radially inward for negative charges. So the positive charges are the sources of electric field and the negative charges are the sinks. Hence that word, sink, right? So if I look at this, the radial electric field pointing outward, it's the same in all directions in terms of magnitude as a specific distance. So if I look at where the cage is, I have electric field lines pointing out everywhere radially outward. What's the angle that those electric field lines make as they pass through the cage? What's the angle compared to the surface of the cage? They're coming out, you could say perpendicular if you want to use the word, or you could say 90 or pi over 2. They're coming out everywhere perpendicular to this cage, aren't they? So they're everywhere perpendicular. So if I drew a cage right there, then I see that the electric field is everywhere coming through here is perpendicular to that cage because of the symmetry that I chose. Now imagine taking the same cage and the same rod. And now I place the rod right here near the edge instead of the center. The electric field as it comes out from the rod remains the same, but this imaginary cage now is not symmetrically centered. The electric field coming out to your right is much larger when it passes through the cage area. And over on your left, it's much smaller because that's like 10 times further away from the rod. Is the electric field perpendicular everywhere as it passes through the cage surface here? No, it is not. So sometimes when you imagine these kind of surfaces, it's very important for you to pick which location and what type of this kind of surface do you want to consider. You can imagine if you put this surface where the cage is symmetric, centered on the rod, that calculation is rotationally invariant. It doesn't matter where you are around the cage, you're going to get the same electric field perpendicular to the surface with the same magnitude everywhere. But if you pick the surface to be offset, no longer true. Makes a calculation about the electric field passing through the surface of this cage much harder, doesn't it? You got to pick it. You get to choose. So these are all things that are up to you as you want to pick the math you want to do to handle the physics on these things. Okay, let's get a volunteer and we'll take a look at another geometry instead of just a rod. Okay. Oh, have you helped, sir? You have helped. Have you helped, sir?
No.
Come on up. Give us a hand. Or an arm, or whatever it takes. Hi, I'm Roger. Brent? Hi, Brent. Come on down. Now, we did a little shock stuff yesterday, little shock therapy, right?
Yeah.
And we're going to do that again. And so I want you to get comfortable with it in case it zaps you a little bit, okay? It might be a little drier today. It might not be a little drier. So take your arm and just tell me, do you feel anything? You feel it yet?
Yeah.
Okay.
Right.
All right. So let's use your arm as a judge, okay? And you can come here and stand there if you like. Okay, so Brent is going to kind of guide you into what he feels for the electric field strength around this sphere. I want you to look at it with the idea of going around with your back of your hand or something and feeling, all right? And what we want to do is he's feeling some kind of electric force here, right? We could see the filaments of the plastic getting repelled from each other and from the sphere. So we know that there are electric forces. We saw that the filament was picked up against gravity, so there are electric forces. Now, Brent's hand, this is a hand. What is it made of?
Water.
A lot of water, isn't it? And a few other things. So, are there properties in the hand that are of the electric field issues? Of the electric, right? Dielectric, of the electric. Are there dielectric properties in this hand? We saw from the electrosurgery example yesterday that there was electrical conduction was possible. Currents flowed. Electric currents flowed in saline solution. Brent's hand is not too different from that. You have sodium chloride in you, and potassium chloride, and a few other things, but I don't know biology. I don't know too much about biology. But he has some of that in him. And they are ions and electrons free to move a little bit, although, yeah, you're just going to get chalked and it's going to be unfashionable.
Okay.
So when he takes his hand and he puts it here, if there is an electric field, it is going to push some charges away in his hand and pull the opposite sign charges towards the sphere, isn't it? So he will feel a little bit of that. I feel it most readily in the hairs on the back of my hand. Oh, tip your head down. You can feel it in the hair in your head.
Can.
Did you?
Yeah.
Whoa! That's cool, isn't it?
Yeah.
One way to straighten your hair, right? Okay, so now what I want him to do is use his electric field detector. Oh, why don't the charges here that get pulled towards, why don't they just leap over there? They're attracted, but they come to the edge of the hand and, oh, there's an air, right? And since they're not dead yet, the air doesn't get it. Okay, so now let's go with putting your hand there. Go a little closer, a little closer, a little closer. And now you hear the spark. Can you hear that? Can you hear it through the mic? I don't know. Do a little closer. That's okay, it just sparks. Okay, you hear that? So now the air is breaking down, and there is some transfer of charge between the sphere and Brent's hand. Okay, back her off. That was pretty exciting, wasn't it?
Very.
Okay, yes. Are you all charged?
I think so.
Yeah. So, all right, so now let's see. I want to feel about, this is a sphere. We're putting the charge on the sphere. We said yesterday that by logic, the charge should distribute somewhat uniformly around that sphere, making the electric field inside the metal zero. If it's uniformly distributed like that, Brent should see the electric force that he feels be independent of angle around and only depend on distance away from the sphere. Do your magic. See if that's the case. Go up above 2. How does it feel?
It feels like there's a lot of static in a very like uniform area around the sphere. It's like a static ball.
A static ball. Okay. And it seems like it's independent of angle as you go anywhere around at a given distance.
It feels like.
And is it stronger as you get closer and weaker as you move further?
Yeah.
Okay, so now instead of guessing that the charges were uniformly distributed, we've established that the field is uniform, depends only on distance, by a very simple measurement. And can you communicate with the spirits?
No.
You guys, he just heard the voice of nature. Nature was talking to him here. Do the hand thing, right? He's hearing the voice right now. See? That's what I'm talking about. I want you guys hearing voices like that. Isn't that cool?
Yeah.
Okay, let's try jumping a few of these guys. Why don't you open that up, get a little sprinkle, let's see how far we get with it today. How far did we get yesterday? What was the best leap? 20 centimeters was the best leap. Okay, go ahead. No better today. Okay, that's the excitement. The excitement. Okay, thank you very much. Good job, Brent. Oh, I wonder if it was turned all the way up. Oh, it was. Darn. Let's see. Now I made another assertion that the electric field inside the metal would be such that charges, given time, the charges will move to make an equilibrium where they are not accelerated, and the electric field must be 0 in the metal. Let's check on that. Okay, we did Brent over here, so male first, female next. You helped already, didn't you? Have you helped, madam?
Me?
Yeah. Would you come on down and add a little spark to our discussion here? Actually, there'll probably be no spark on this demo. None whatsoever. Okay. So you are?
Fanny.
Fanny? Hi. Roger McWilliams. Hi. Okay. So now let's do this. Can somebody give me a sheet too? Here, you can have that. Can I have another sheet? Thank you. Let's make it a little easier for you guys to see this. So Fanny, take that and then just, do the charging thing like that. And you should be able to see a little better, I think, if I hold here like this, right? Okay. All right. Now, let's go ahead and touch that to this piece up here. Or just across the top, who cares? And go ahead. Such an excitement. Oh, goodness sakes. Let me try. And okay, so, there's Gauss Dominus. Okay. Oh, idiota. Okay. Now it's better. Okay. Now I have to discharge the damn thing. Okay, here we go. Do you see that the two needles are near each other? So there's one needle that has its weight slightly below the pivot point so that gravity will bring it down. And then there's the second needle which is fixed to be in the vertical direction. And right now, from a distance, you probably just see one needle because they're parallel and vertical to each other. Okay, now do that. And now put it on here. Okay, so Fanny, is that right? And Fanny has done this. Okay, take that away. And the charge is there, and you see how they're repelled, right? So there is charge that moved into this. Okay, the charge did move in there. Now I'm going to discharge it. Put this guy up there, and it's contacted. Oh, that thing, the little switch moved again. Let's do that. Okay. Let's hopefully it won't do that. Okay. Now do that.
Again.
Yeah, and touch it to that. What happened inside? Nothing. You are getting sleepy. It could be true. Nothing happened. But there was charge on this. Do that again. And let's try putting it over here on the cage. What happened? Nada, niente. Jumping Jehoshaphat. It must be that the electric field is zero inside. No charges were moved into the center there to charge that up, and the electric field stayed zero inside. So when you put charge onto a metal conductor, as Fanny so adroitly did, then the electric charges distribute themselves primarily towards the outside, but in such a way to make the electric field inside a conductor zero. So now I could go, I can't, aha. It's okay. I have daughters. They don't like their hair messed with.
Josh.
Come here. Now, if we put Josh inside.
Yeah.
Okay? Now.
Stand up.
Yes, stand up. Now, turn around. Okay? Now, if we put charge on the outside here, what will be the electric field inside? Zero. So we can protect ourselves. We can put on the sheath of protection by putting a metal cage around us. Thank you, Josh.
No problem.
I appreciate it. This allows us to have electric field free, even if the electric charges were out here, electric fields are out here. Yes?
Sorry, what was the reasoning behind that again? Why it's zero instead?
Okay, the reasoning behind is if there's an electric field, an electric charge will feel it. If electric charge feels an electric field, it moves. Electric fields accelerate electric charges. F equals QE. That's the basic place to think from, right? So if E is non-zero, any Q present will be accelerated. Attached to that is the knowledge that there are electric charges in conductors. There are electrons in conductors that are fairly free to move. That's why they're called conductors. And so those electrons in this, or any that we add to it, if there is an electric field, will move. Does that do it for you? Okay, so now we can put on our cloak of invisibility for electric fields. That is called a Faraday cage. Faraday, as in Michael Faraday, as in one of the top 5 contributors to the world in all of the time the world has been spinning. Okay, I put Michael Faraday and James Clerk Maxwell in the top 5. I don't want to put them top 1 and 2 because then I get in fights with people. Okay. I'm thinking, Fanny, that may have been the full excitement for you.
Okay.
Is that, do you want to, while you're here, why don't you just feel this guy? I mean, do you trust Brent?
Yes.
No, you do not trust
I know.
Brent. Come on. Just, see? Not,
I feel
it'll spark, but it's just, see, it's not a big deal. Okay, now, just stand on that. Stand on that. Put your hand right on top. Just go bam and hold it there. Don't let go. Now shake your hair. Do you feel it in the hair at all? No? Okay, now let's try this. Take your hand, see if you, no, leave that one on there, and bring your other one over and see if you can spark me. Right here.
Oh.
Does it spark? Oh! Whoa! That's more exciting than putting socks on a rooster.
It's pretty strong.
Okay, yeah, okay. Let's go. Go for it. Okay, that was cool. Oh, should we? Let's see what we can do here. Come on around. No, it's fine. You're fine. You put your hand on there. Okay. Now, you grab my hand. Let's see if we can zap him. Oh, gosh, just now. Hold on. Yeah, you ready?
Yeah. Nope.
Ah. Okay. The reason is, why did it not spark over here, but it did spark me?
Were you not strong enough?
I am so grounded in life that, well, Fanny, show them what you're standing on.
It's wood.
With plexiglass underneath for the feet. So she was ungrounded. She was floating. As we say, electrically floating. My feet were on the ground here and conduct the electricity through the floor pretty easily. But when she stands on here and attached to there, it's like her body is, go ahead and sit down, thanks. Her body, and you can also sit, I think we're done. Unless you want to play more with that. Okay, so when Fanny is standing on the platform that made her float, some of the charge got transferred from that sphere to her body. She was an extension of the sphere. Her body had some capacity to store charge. Capacitance is going to come up. Her body had some capacitance, some ability to store charge. Then, because I'm standing on the ground, the current can flow from me into the ground, and it left no excitement for you, right? Oh, but I missed it. I should have had you spark directly with Fanny. That way, boy meets girl, it's that kind of thing. Okay, so anyway, let's take a further look here at this kind of stuff. Now we've done it for a sphere, right? A sphere, and our observation is the field is the same at any given radius, independent of angle around it. It is not something we are speculating. It's not something that is just chalk on the board. It is Brent's observation. It's an observed truth, okay? We will call this Brent's Law. It was Brent, is that right?
Yeah.
Oh, you love it, don't you? Okay. And Fanny gave us the shocking truth. Okay, so there we have it. The sphere, okay. Now I want to make a surface around the sphere. And I'm drawing on a two-dimensional board, so I want you to imagine that it's a three-dimensional surface. There's a sphere of charge plus Q. Charged sphere. So we have a charged sphere here. And we have charge Q spread over that sphere. We have noticed Brent's observation was the electric field was everywhere perpendicular to that metal surface. Everywhere perpendicular to the sphere that he held his hand at. So the electric field goes out like this, not because we have some fancy mathematical equation that tells us, but because we observed that electric charges cause this to happen. And it's everywhere perpendicular. Now I want to go back to the concept of the small discussion we had at the start of yesterday's lecture, or whenever, about the rain coming down and the flux of the rain. If I want to calculate what is the electric field times the area and then add it up over the dashed surface. If I want to find that, what do I need to do? Let's see now. Let's take some electric field and imagine the surface. We're going to use this piece of paper as the surface. Nancy, you there? If we were to say that this orientation, the paper was pointed towards you, we could use a description by putting a unit vector on the paper, on the surface that's perpendicular to that surface, and it's pointing at Nancy now, isn't it? And so the direction of the paper is known. Now, as I rotate the paper, you see a different area, don't you? You see less silhouette. And if I get it to here where it's 90 degrees, what surface of the paper do you see? Just this edge. And the area goes to 0 when this unit vector is 90 degrees from Nancy's vision. Right? So I can use this unit vector perpendicular to the surface to describe the direction of the paper. Even though it's just an area, it has a direction associated with it. How much area does it have? Well, in standard old American sheets here, it's 8.5 by 11 in inches, right? So there's my area element, 8.5 by 11, which is how much? How many square inches is that? 92, 93, somewhere around there, right? And we have then an area, 93, 90, I'll go with 92 since you suggested it's fine. Okay, so 92 square inches and a direction here. And then, Nancy, you see 92 square inches, don't you? And now you see about 92 times cosine of 45 degrees. Now you see 92 times cosine of 90 degrees, which is 0, nada, niente. So the thing we have to do with this integral is we want to do the integral of E dot dA, where A is defined as I just showed you graphically with the sheet of paper. And thank you for that sheet again. And I'm not done. But wait, there's more. If we look at this surface, what happened to that cage? If I put a charge inside this cage, does the cage go everywhere around it? Or is there a hole in the cage? There's a hole here, isn't there? Right? So if there was some electric field lines that came out through here, and I was just imagining the area on this cage surface, I would miss some of that electric field, wouldn't I? So I want to require that this surface be closed, no holes in it. And I'm going to put a symbol there to indicate closed. We know it's a closed surface because the differential element there is an area. So what we're doing is thinking of a balloon of some kind. You get the choice. Anybody chewing gum here today? Is anybody? You could blow a bubble with that, right? And you could pick the size and shape of the bubble you want to blow. Now, of course, you're limited by the Hooke's Law constraints and various plastic, elastic things. You can't blow something that looks like a little donkey. Okay, but you do have a choice as to what the shape of that bubble is to some degree, right? How big, where, what the surface looks like. This area has to be completely closed, but you get to pick what it is. It's your imagination that does that. I have picked a specific one here which has a high degree of symmetry. Because Brent observed the electric field had the same magnitude at a fixed distance independent of angle around the sphere, I've drawn it to have exactly the symmetry of what he described, where he got everything was the same. So, this application applied to the picture, applied to our sphere, on that sphere, what is the angle of the electric field with respect to the area vector? It's always, the electric field is always pointing straight out from the surface, and dA is always pointing straight out from the surface. So let's put a few of those in. Here's a dA element over here. Here's a dA element if we're up here. And here's one over here. So if you were a small insect crawling around on that surface, wherever you were, you said dA is perpendicular to the surface. It's always pointing straight out radially. And the electric field is also pointing out radially. This dot, this is not a mistake on the chalkboard. What does this represent? The dot product. Remember, I have a times here and then didn't put a vector, so we had to figure out what kind of product we're doing. And this indicates here, we figured it out. It's a dot product. Nancy told us we have to use a dot product. Okay? Now, when we have the dot product for this particular application, what's the angle? Let's think about the one that's going up. Here's the electric field going up. Here's dA going up. What's the angle between them? They're separated by my arm width, but the angle is 0. What is cosine of 0? 1. Unity, right? Okay, so that tells us it's the integral over the area of E dA cosine theta, and this is 1. It's not 0, it's 1. Electric field, same magnitude everywhere around that sphere. That comes out. That's equal to integral E dA. Because the electric field's constant on that surface, we can take it out. Now, here's the hard one. What's the surface area of a sphere? Let's use a little physics to guide our answer. If you look at this sphere right here, what's the area you see? You see a circle which has an area of pi r squared. But then, wait a minute. Everywhere I go, there's more area. As you go around it, it's not just a circle. It has to be more than pi r squared. Play a little golf doing this, and we say 4 pi r squared. And what's the r? That's the radius of our imaginary surface. Going out here, that's this guy. That's how much electric flux is there. So the incremental electric flux is E dot dA. Question?
Did you just define R as the distance from the center of the sphere to the edge of the electrical field, or did you define R as the radius of the sphere?
The R is the radius of the imagined sphere. Whatever your imagination has said for that sphere, that's R. This particular inside charge sphere has some radius also. So you want to be careful. You could have either, right? Okay. So this one is out to the imagined sphere. This imagined sphere has a name. We call it a Gaussian surface, named after Gauss. I suspect, I don't know my history very well, but I suspect Gauss at least spoke German and may have been some kind of precursor of German I don't know what the countries were when he was around. Okay, so the Gaussian surface is the dash thing. Our electric flux increments are E dot dAs. And so the total electric flux is 4 pi r squared E for this particular application. Not necessarily for others, but for that one. Now, if we had no charge on the sphere, we would not feel any electric field. As we increase the amount of charge on the sphere, we make more electric field. And so we see that we might think then that the electric field is created by the charges that are enclosed. And I want to throw in a constant to get the units right. So what we are writing here is this. The electric flux through a closed surface, the net electric flux through that closed surface is equal to the magnitude of the charge that's enclosed divided by epsilon naught. Now, epsilon naught isn't a very big number. It's pretty small. So dividing by epsilon naught is multiplying by a really big number. So this says that electric fields can make pretty substantial effects on things for us, which is nice to see. There is a grave danger here in the way you look at this thing and calculate. This is called Gauss's Law. And it is the first of 4 equations in electricity and magnetism that will delight, amuse, entertain, and provide sustenance to you for the rest of your lives. And if you want to work, you can get a job using them. If you learn them well, you can be paid well. And that will happen over your entire life. I guarantee electricity will not diminish in its importance in your lives. So, Gauss's law is this first one here. Very important to remember the closed element here and that I've put enclosed. One has to be very careful in the conceptual thinking of this. And you notice it basically is just saying Coulomb's law. It's just a different way to say it, but it's a little more elegant, and it will lead to some predictions of things which are a little easier to see than going directly from Coulomb's law. Suppose we have some electric field. So this is a caution. Here is some electric field. And for that electric field, I want to imagine an enclosed surface. It's my choice, right? I'm going to take, let's look at this one. Here's an enclosed surface. You can imagine it's like a spaceship, or it's a sausage, or it's a balloon, or a bubble. Anyway, here's the surface, and there are no holes in this surface. Is the electric field here 0? What do you see from the drawing? The electric field is not 0, is it? There is an electric field. So, now we apply this Gauss's law. Here's our dA pointing out, and here's our dA over here pointing out. The direction of the electric field on the right is going out of the surface. So dA and E are in the same direction. What's the cosine factor for that? 1. E dA times 1. Going in over here, Here's E going this way. dA is over this way. What's the cosine factor here? -1. They're oppositely directed. This one has a minus contribution. The E field's about the same on both of them. This one goes minus on this guy. This goes positive over here. What do they add up to? 0. They add up to 0. But the electric field is not 0. This is telling you, in Gauss's law, not the magnitude of the electric field, but the flux through the surface. This law is saying that electric charges make electric fields. That's the word's interpretation. Electric charges make electric fields. But the electric field doesn't have to be 0 if there are no charges enclosed. You could have had the electric field made by something outside where your surface is. So here we have electric flux equal to 0, but E is not equal to 0 because the charges that made the electric field were not inside that surface. So this tells you the contribution to the electric field by the enclosed charges. Be very careful in life. You think I'm just looking here, and you're looking microscopically what's there, but just like the hydrocarbons that power the Tesla battery-powered car, look around the corner and see what's plugged in over there. The hydrocarbon source is around the corner, and if we had electric charges over here, they make an electric field that passes right through this region, even though we didn't have any enclosed in what we were imagining. Okay? So when you set these things up, always ask yourself, is there some external source of charges to make electric field that's not calculated just with the Gauss's law approach? Okay? That one people forget a lot. Is there an electric field here at the surface of the Earth?
Yes.
Yes, there is. The Earth is charged. What's the direction, do you think, of the electric field? Perpendicular, up or down, right? Depending on what sign of charge is on this giant sphere, our pleasant orb, right? So it's perpendicular to the surface of this giant conductor that we stand on. Interesting point. And suppose that the electric field at the surface of the Earth was maybe 10 newtons per coulomb. If you know that, could you say what the charge is that's on the Earth? Ah, yes, maybe so. So we observed that E is perpendicular to a conductor surface So if we have some kind of conductor, there's a conductor. We're going to put some charge on this conductor. So we go this kind of looks like an amoeba, doesn't it? So we put some charge on this conductor, just like what Brent observed, and Fanny as well observed. The electric field points out, everywhere perpendicular. How big is it? We already know the answer. If we have this charge here, that charge will move around to make the electric field in the conductor equal to 0. And I want to think about just this one little part. If you get small, put on your electron hats. Okay, everybody, let's see it. Put on your electron hats. I got a few participants. Come on, get them on there. That's right, you got your electron hat on. You shrunk down really small now, okay? And we're looking right here, and you look around, and you see the electric field is 0 inside, and you're not being accelerated sideways. So you see that there is some sigma on that, right? Sigma coulombs per square meter. And sigma is a function of position. Oops, let's do it with these kind of coordinates. Okay? It does not have to be a constant. It can be a function of position. Depends on the circumstances what it will work out to. But when you're there, you look around you and you see a sigma. You've got your electron hat on and you're looking around, you see a sigma. The electric field just outside, on the outside, outside the conductor, outside at the conductor, is sigma over epsilon naught. Yesterday, we did a calculation for a sheet. And we found that the electric field above it was sigma over 2 epsilon naught. The electric field below it was sigma over 2 epsilon naught. Have I lost my mind? What happened to the 2? Well, I think the answer to the first part is yes. But the 2 I got right. Because now, on this one, the electric field pushes out from this sheet. Well, this charge also pushes electric field the other way. However, since the electric field is known to be 0 inside, it means that all the rest of the charges here have an electric field contribution which exactly adds up to exactly sigma over 2 epsilon naught pointing inward here, but it's pointing this way from all these other charges. So this charge makes a sigma over 2 epsilon naught contribution right here at the surface, and all of the rest of the charges make precisely the same. That makes it sigma over epsilon naught, and because I find that exciting, you know I have lost my mind. So we got both questions answered. Okay? Okay. Are we excited? Now this is a physics class. Are we excited? Yeah. I think the answer for some of you in this moment is, that's a negatory, sir. Is that right? Yeah, you guys, come on, get with it. Okay, so this Gauss's law we need to really work with because that's the conceptual basis. Electric charges make electric fields. For homework tonight, what I want you guys to do is go read a Shakespeare sonnet. There aren't a whole lot of them. Most of them are kind of depressing unless you pick the portion of it you want. But they are exquisitely beautifully written, short little equations. Pick a Shakespeare sonnet and read it. And then what I want you to do is look at this kind of stuff. We're going to have 4 equations. And at the end of this quarter of work, those 4 equations represent some of the most beautiful prose ever presented on this planet. And I want you seeing the beauty of these 4 equations that we've got and compare them with Shakespeare. Okay? Now Shakespeare has in Shakespeare every motive and method known to humanity. Every emotion and motive, all that stuff is in there somewhere. All the good and bad. These equations give you everything about electricity and magnetism, all the good and bad. Okay? So you're going to be doing that stuff and using it the rest of your lives. I want you to know that. Do we have further demonstrations? No. Did we do all of Gauss's law? Do you have any questions about Gauss's law and electric field calculations? You could similarly make calculations of flux for the rain. And it would guide you about how to hold an umbrella, wouldn't it? The same dA. If rain is coming down, do you hold the umbrella over here? No, because the dA of the umbrella says, oh, flux, not blocked, need to block, right? Okay? All right. I think we're done for today then. Come down and feel the fields here. Let the force be with you. Fanny, thank you for helping. Brent, thank you for helping today.